Well, to continue with our discussions on the analysis of the slug flow pattern. So, till yesterday what we did? We found out that for the slug flow pattern, the relative velocity or the drift velocity UGJ, that was a constant, and this was nothing but equal to UG minus J, where the since all the gas is confined as your slug flow. If I show you the idealized version which I had mentioned in the last class. Yeah. If you see the transparency of the where I had shown you the unit cell for your slug flow analysis in a vertical tube, we find that the slug flow pattern, all the gas we assumed was confined as Taylor bubbles. So, therefore, u b and the velocity of the bubble can be taken as equal to the velocity of the gas during the slug flow pattern. So, therefore, this is equal to u b minus j. Okay. And we found out that u g j was constant, and therefore, this will be equal to the velocity of a single bubble when it is rising in a stationary liquid, or this is equal to u g at j equal to 0, which can be defined as u infinity, is not it? So, just again I would like to remind you that this u infinity has got a different nomenclature as compared to the u infinity which we have referred in the bubbly flow pattern as well as in the drift flux model. Okay. So, from there we found out that u b, this is equal to u infinity plus j, is not it? Or in other words, the thing was that in terms of, suppose we would like to write it down. So, therefore, this u b was u infinity plus j, and accordingly alpha we could find it out as, this was nothing but j g by u g, which is again j g by u b, which is nothing but j g by u infinity plus j. In terms of the volumetric flow rates of the individual phases, this gives us q g by q l plus q g plus a u infinity. So, till this much I believe we had done in the last class. Okay. Now, that time itself I had told you that the situation is not as simplified as I had mentioned it. There has to be several corrections under different flow circumstances. For example, the first thing which comes to the mind is, we had assumed that the bubble rise velocity is equal to u infinity plus j. Okay. What do we assume? That the entire liquid in the front of the bubble, this particular liquid, the entire liquid flows at the same average velocity j, but usually it does not happen. For turbulent liquid slugs, we can have a flat velocity profile, but otherwise we will be having some sort of a velocity profile, and due to this existence of this velocity profile, since the bubble tip is directed at the center of the tube. So, there will be a tendency of this bubble tip to rise with respect to the center line velocity of the liquid slug rather than the average volumetric flux of the liquid at the cross section ahead of the bubble. Correct? So, therefore, depending upon the velocity profile, what we would like to do? We would like to introduce a particular correction, say C1j, okay, where C1 accounts for the effect of the or rather it is a measure of the fact that the bubble does not simply move relative to the average liquid velocity, but a weighted average velocity. You remember when we were doing the drift flux model, how I had introduced the term C0? If you remember, I do not know whether you remember it. I had shown you alpha j is not equal to the average value of alpha and the average value of j. So, therefore, the ratio was taken as a constant. Why? Because the average value is not always important, the weighted average, and from there we had introduced the weighted average velocity, which is different from the cross sectional average velocity. So, from those particular things, if you remember, we find that a correction C1 has been introduced here, where C1 it is nothing but it is the measure of the fact, that bubble rises not relative to average velocity, but relative to weighted average velocity. Okay. So, therefore, we have to introduce a correction factor. Now, remember in the drift flux model also we had introduced a correction factor C0. Now, both these factors, this C0 and C1, they more or less they have the same sort of a meaning, and they also usually take up the same sort of a value. Usually we find C1 it is equal to 1.2, but remember that although the physical reasoning behind the derivations are same for C1 and C0, but basically they are different parameters. Okay. It is just like your volumetric flux and your velocity. Okay. Normally superficial velocity and volumetric flux, they have the same mathematical expression, but their meanings are completely different, and if we really refer to a 3-dimensional vectorial form, then they would be having different sort of physical interpretations. It is just like that. Both of them are volumetric flow rate divided by the total cross sectional area, but the definitions are completely different. One means the volume flow rate per unit cross sectional area, and the other is the velocity which that phase would have if it would have flowed alone in the pipe. Accidentally for 1-dimensional flows, both of them take the same mathematical expression. It is sort of this. Okay. The other thing which should come to your mind is, see, suppose we are having Taylor bubbles more or less close to one another. Suppose these bubbles, they are more or less close to one another, then in that case what happens? There is a wake effect behind this particular bubble. Why this wake comes? Because this downward flowing liquid film, it has to mix with the liquid slug which is travelling upward. As a result, as I told, a wake region is created, and therefore lot of small bubbles are sheared away from the tail, and this becomes an aerated mixture. Okay. Now, when these bubbles are not sufficiently placed away from one another, then definitely the preceding bubble, that is going to influence the succeeding bubble, and the succeeding bubble, what it tries to do? It tries to travel faster so that it can reach the preceding bubble, coalesce with it, and then become a bigger bubble. Okay. So, therefore, there is another effect also which we should consider. That effect is the wake effect of the preceding bubble. Okay. Now, remember one thing, in this, if there is a wake effect, then in that case this UGJ, or in other words, that cannot be made equal to U infinity. Why? Because U infinity was the velocity of a single bubble in a stationary liquid column. Now, the velocity with which a single bubble would travel might not be equal to the velocity which it would have if a number of bubbles are placed one above the other and they are travelling, because each bubble would try to influence the succeeding bubble. Due to the wake effect, they would try to travel faster. Okay. So, therefore, UGJ is not strictly constant as we had assumed it to be. Why it is not strictly constant? Two things. One is that this J is not, or rather the bubble does not rise with respect to J, but with respect to some particular weighted average J. Secondly, that this particular U infinity, this may not be applicable for the present situation, for a number of bubbles are flowing one above the other, and there is a wake effect of the bubble. So, therefore, this also has to be corrected for a correct or an accurate expression of UB. So, therefore, this is also corrected by a particular correction factor, say C2. Okay. Where C2, if I write it down, this C2, it is the measure, more or less you will get these in books, but probably not in the form that I am teaching you. In the books, it is slightly more haphazard, that is what I have felt. So, if you follow the notes and then refer to the book, probably it will be simpler for you to follow it. Okay. So, therefore, we find that C2, it is a measure of change in relative velocity, due to approaching velocity profile. Okay. So, therefore, we find that usually what we find is, so therefore, finally, this UB, this becomes C1j plus C2 U infinity. Now, if we substitute this expression of UB into the expression of alpha, then in that case what do we get? We get alpha, this is equal to QG by C1 QL plus QG plus A C2 U infinity. This is the corrected expression, isn't it? When we account for the wake effect of the, or rather the measure of the change in relative velocity due to the approaching velocity profile, as well as the considering the fact that the bubble rises not with respect to the average velocity, but with the weighted average velocity. Okay. So, this is the final expression that we get. Now, usually it has been observed that for fully developed flow in circular pipes, when REJ means, remember, this is the liquid flowing at velocity j, okay, or in other words this is d j rho L by mu L. When this is greater than 8000, normally we get C1 equals to 1.2 and C2 equals to 1.0. That means, under that conditions we assume that more or less the bubbles are sufficiently placed away from each other, or in other words the liquid slugs between the intermediate Taylor bubbles, they are large enough such that each particular bubble does not influence the motion of the succeeding one. Okay. So, under such circumstances, for fully turbulent flow, fully developed flow in circular pipes, usually we have C1 is given as 1.2, the same value as C0, and C2 equals to 1.0. And for laminar flow we find that the theory is still not very well developed and accepted correlations for C1, C2 not available. Okay. The theory is still now not well developed and accepted correlations for C1 and C2, they are not yet available. One particular thing is, usually what people say is that C2 it depends upon the spacing of the bubbles. So, therefore, it should be a function of liquid slug length, isn't it? So, if it is a function of liquid slug length, people have proposed expressions of this sort: 1 plus 8 e to the power minus 1.06 Ls by d, okay, where your Ls is the liquid slug length, or in other words it is the bubble separation length. Okay. People have also observed that for the case of boiling, C2 equals to 1.6. Okay. For laminar flow, when it is turbulent flow, fully developed circular pipes, then C2 equals to 1.0. For laminar flow, accepted correlations are not available, but more or less we can take C2 as this, and for that particular case usually the velocity is parabolic. So, therefore, we can assume C1 to be equal to 2.0 as well. Okay. And when flow boiling takes place, for boiling, we can take, people have assumed C2 to be equal to 1.6. Okay. So, these are the different values which people have assumed, and accordingly people have tried to modify the expression of alpha in order to find out, or rather in order to substitute this particular alpha. In fact, I should have written it in this particular form. It is actually the cross sectional average alpha, okay, where this is nothing, if you remember, this is nothing but integral alpha dA by integral dA. Okay. So, therefore, this is the cross sectional average value of alpha. The corrected value can be obtained from this particular form. Okay. Now, this alpha, if we substitute it in the pressure drop expression, then we should get an expression of the pressure drop to, or rather to the expression to predict pressure drop for the slug flow pattern. Okay. Now, under normal circumstances, if you remember, how did we start the derivation? We started the derivation by considering negligible wall shear stresses. Okay. From that only we had found out that J21 is independent of, or rather it is a function of alpha only for the drift flux model. As a result, UGJ is a function of alpha only. Entire thing was started, if you remember, in the drift flux model for gravity dominated flow situations where wall shear stresses are negligible. For vertical, we are doing the vertical slug flow. For slug flow in vertical pipes, this is quite a reasonable assumption. isn't it? So, therefore, we find that the pressure gradient in this particular case, this should be minus dp dz. This should predominantly consider or consist of the gravitational pressure gradient, which is nothing but g into alpha rho g or alpha rho 2, whatever you may write, to 1 minus alpha rho L, where this alpha can be given as I have already told you. This is nothing but the area average, this is nothing but C1 QL plus QG plus AC2 U infinity. Okay. So, therefore, in order to find out alpha, which can be substituted in the pressure gradient expression, we need to know u infinity, and how to know u infinity, that we have already discussed. All the other things, if you find, they are all input parameters. Okay. So, for most of the cases we find that the pressure gradient, it comprises of the gravitational pressure gradient, under which situation we find that it can be found out from this particular situation. Now, suppose wall shear stresses are important. Under that condition, what will we do? If wall shear stresses become important, now just try to remember, just try to observe the unit cell which I have shown in this particular slide. Now, if wall shear stresses are important, then we find that there are wall shear stresses all through the pipe. Achha. In the Taylor bubble region, the liquid flows downwards as a liquid film. Agreed? So, therefore, in this case, the wall shear stress will be acting in the upward direction. Again, if you notice the liquid slug, the wall shear stress, the liquid slug flows up, wall shear stress will be in the downward direction. So, therefore, it is not very easy to find out the wall shear stress in this particular condition. Okay. So, what will be preferred to do in this particular case? Since it is not very easy, certain things we can assume. First thing which we can assume is that, see, in the Taylor bubble region, more or less what do we find? We find that liquid film is very thin, and this nose region is also quite small compared to the cylindrical portion. In the nose region, what happens? The liquid, it accelerates from 0 to some particular value, which is a function of the distance from the tip of the nose, or in other words, at any particular distance, say h from the tip of the nose, the liquid film velocity will be root over of 2gh, laws of motion, isn't it? And but moment it reaches the tail region or the intersection of the nose and tail region, this particular nose region, it is quite small. After that, it flows at a constant velocity, it attains a terminal film thickness, and it flows down at a constant velocity. When it is flowing down at a constant velocity, that means the wall shear, it completely balances the weight of the liquid. Yes or no? It must completely balance the weight of the liquid, due to which the liquid becomes a free falling film under this condition. Now, if the wall shears is contributing to, or rather it is serving to balance the weight of the liquid, that means that it does not contribute to the pressure gradient. Or in other words, we can assume that the contribution of the wall shear in the Taylor bubble region, where the liquid flows as a film, is negligible and can be neglected, and we can assume that the wall shear primarily arises in the liquid slug region, where the liquid slug, it flows as pure liquid upward. Do you agree with me? Or anyone who wants me to repeat this particular part? What happens, you just try to see. Slug flow is occurring, okay? Liquid Taylor bubble, liquid slug, Taylor bubble, liquid slug. This is occurring in a vertical pipe. When it is occurring in a vertical pipe, then what are the components of pressure gradient normally? We have gravitational pressure gradient, frictional pressure gradient, acceleration pressure gradient. Acceleration pressure gradient, it arises only when there is an area change or when there is a phase change. Usually under these two conditions they arise, or there is a very rapid pressure change, due to which the compressible flow or compressible fluid, it undergoes a volume change with distance. Under these conditions it arises. Under normal circumstances, we can assume that acceleration pressure gradient can be neglected if the pipe is not very large, if there is no phase change, and the two fluids flow through an area of constant cross section. Agreed? So, therefore, the predominant, what are the two predominant? Gravitational and frictional. When the pipe is vertical, quite naturally the gravitational pressure gradient is much more important. In fact, most of the time we neglect frictional pressure gradient for vertical pipes when only a single fluid is flowing through it. Frictional pressure gradient usually comes when the pipe is horizontal, that we have already seen for single phase flows. Two phase flow, sometimes it is quite important, because in this particular case your frictional pressure gradient arises not only due to the friction between the fluid and the wall, but also due to the interfacial shear as well. Okay. Now, for vertical pipes under normal circumstances slug flow is occurring, we can assume quite safely that the frictional pressure gradient is negligible as compared to the gravitational pressure gradient. Okay. Under that circumstances, what do we get? We find then the total pressure gradient can be obtained from the expression that I have written down here. If wall shear becomes important, under that circumstance what do we do? Now, if wall shear becomes important, then definitely we have to consider the frictional pressure gradient across the wall. Now, remember one thing, frictional pressure gradient changes across the wall, since the frictional pressure gradient or rather the wall shear is different in the Taylor bubble region and in the liquid slug region. It is different not only in magnitude but also in direction, a very important fact which usually does not occur elsewhere. In one particular pipe the wall shear is changing, this is really not a very common situation. Okay. What do we find? We find that the wall shear in the Taylor bubble region, it acts in the upward direction, that means the direction in which the Taylor bubble is rising. Why? Because the liquid film is flowing downwards here, and in the liquid slug region it is in the downward direction, because the liquid slug is flowing in an upward direction, right. Now, we find that the wall shear, then finding out the wall shear or finding out the frictional pressure gradient, it is not at all going to be very straightforward. We have to find it out for this particular region, for this particular region it becomes quite complicated. But fortunately, we observe certain other things as well. What do we observe? We find that for most of these cases, the Taylor bubble can be approximated as a cylinder of constant cross section which has a constant curvature in the flow direction, isn't it? Therefore, and the gas density and viscosity are negligible as compared to the liquid density and viscosity. Agreed? Therefore, the bubble surface can be assumed to be a surface of constant pressure. Therefore, the interfacial shear here can be neglected. So, interfacial shear part gone in the Taylor bubble region. What rest is remaining? Wall shear. Now, in this particular case, think one thing, what is happening? The liquid is flowing as a film. The liquid may be at the tip of the nose, it has a 0 velocity and then it accelerates downwards along the nose. The film thickness increases as well as the velocity increases till at the intersection of the nose and the tail, the film thickness it becomes constant and the liquid film attains a terminal velocity. And then after that it falls at that particular constant velocity, it behaves like a free falling film. More or less, if the Taylor bubble is reasonably long enough. Why? Because if it is reasonably long enough, the cylindrical portion will be larger as compared to the your hemispherical portion. Okay, if they are very small Taylor bubbles, then it comprises mainly of the hemispherical portion, just like cap bubbles. Under this condition, this particular assumption does not hold. It holds only for more or less long Taylor bubbles, where we can assume that the Taylor bubbles are cylindrical just because the nose region is much smaller as compared to the tail region. Agreed with me? Now, under such circumstances, what happens? In the tail region, the liquid becomes a freely falling film. When it becomes a freely falling film, that means it is not acted by any net unbalanced force. So, under this condition what happens? We know what are the forces acting on the liquid film. It is the weight of the liquid film pulling it downwards and the wall shear which is pulling it upwards. When it becomes a freely falling film, that means when it falls at a constant velocity, from mechanics we very well know that means it is not acted by any net unbalanced force, or in other words the wall shear completely balances, or the wall shear force completely balances the weight of the liquid film. Agreed with me? Satisfied? So, if the wall shear is contributing totally to compensating the weight of the liquid film, how can it contribute to the pressure drop or the pressure gradient? Can it contribute? So, therefore, we can very safely neglect the pressure gradient which arises due to wall shear in the Taylor bubble region. We can very safely neglect that particular portion, and we have to consider only the wall shear or rather the frictional pressure gradient which arises in the liquid slug region. Liquid slug is just pure liquid. So, therefore, there the frictional pressure gradient which arises can be found out from the single phase fluid dynamics itself. Yes or no? So, therefore, for this particular condition, what can we write? We can write that tau w, this is nothing but FL rho L j square by 2 in the liquid slug region, where FL is a function of, it is a function of REL at j velocity, or it is a function of j d rho L by mu L. Agreed? Isn't it? So, therefore, under this particular circumstance, what is minus dP dz frictional equal to? Just as I had done it in the previous class, this is nothing but 2 rho L j square by d. Yes, sorry, 2 FL rho L j square by d. This is the frictional pressure gradient at the liquid slug only. Agreed? And we can assume that since the entire gas flows as Taylor bubble, liquid slugs occupy a portion 1 minus alpha of the pipe volume. Yes or no? Therefore, the minus dP dz frictional for the entire pipe, this should be equal to 1 minus alpha into 2 FL rho L j square by d. Yes or no? Agreed? If this is true, therefore, what happens to the expression of the total pressure gradient? The total pressure gradient, therefore, it becomes minus dP dz, this is equals to minus dP dz gravitational plus minus dP dz frictional, which is nothing but equal to g into alpha rho g plus 1 minus alpha rho L plus your, I will write it down, plus 1 minus alpha 2 FL rho L j square by d. Can I write it in this particular form or not? Yes or no? Agreed? Now, let us see if we can do something else. What do we know? We know rho g is much less than rho L. Do we know this? Do we know this? If we know this, then can we write down rho m, it is almost equal to 1 minus alpha into rho L? We can do it. So, therefore, in place of this particular rho L, we can substitute it with rho m by 1 minus alpha. Why I want to do it, I will tell you. So, therefore, your frictional pressure gradient, this becomes 1 minus alpha 2 FL 1 minus 2 FL rho m by 1 minus alpha j square by d. Can I write it in this particular form? Or in other words, what does it become? It becomes 2 FL rho m j square by d. Does it become this? And have you ever come across this particular expression? Are you aware of this particular expression? What is this? What is this particular expression? It is the frictional pressure gradient that we had obtained from the homogeneous flow theory. Correct? So, therefore, we find that this is the homogeneous flow frictional pressure gradient, where you have to remember one thing, in this frictional pressure gradient, how is it different from the homogeneous flow value that we get? The alpha which we use to calculate rho m, that alpha has to be calculated from this particular equation. This will give us a value which is different from the homogeneous flow value which we obtain for under this flow conditions. Is it clear to you? So, therefore, what do we find? The final expression of minus dp dz is g into rho m plus 2 FL rho m j square by d, the same expression that we had got for the homogeneous flow model. Just we have to remember that how it is different from the homogeneous flow model. It is different just in one way, that the alpha which is used to calculate rho m, where this is the expression of rho m, the alpha which is used, that has to be obtained from this particular expression, which has been obtained from the slug flow pattern using the concepts of drift flux model. Correct? Now, how to know that whether you have to consider the frictional pressure gradient or not? What you are supposed to do? You know the flow conditions, inlet flow, pipe diameter, everything. Just you assume that what will be the pressure gradient if the flow was homogeneous. Definitely for slug flow, the pressure gradient will be less or closer to it. So, what you do? You first find out the frictional pressure gradient for the homogeneous flow model. Then you compare it with the total pressure gradient or the gravitational pressure gradient. If it is much less, you forget about the frictional pressure gradient. You simply assume that the total pressure gradient comprises of, or the total pressure drop comprises of the gravitational pressure drop, proceed along with it. If you find it has got a substantial amount, friction contributes substantially to the pressure drop, then in that case what you have to do? You have to use the alpha which you have found out for the slug flow model, then that alpha has to be used, and accordingly the frictional pressure drop has to be found out and it has to be included here. Agreed? And now what about the acceleration pressure drop? Now remember one thing, more or less when you do not know anything, then what you have to do? We have to resort to things that we know. That means we have to assume, suppose it was homogeneous flow model, then what would have been the acceleration pressure gradient? Usually, as I told you, for round pipes, constant cross section, no phase change, not a very large pipe, it will not be very much. Okay. But remember one thing, you have to be very cautious when you use the expression of acceleration pressure gradient as obtained from the homogeneous flow model to find out the choking conditions for slug flow model. Definitely, you will not get the correct choking conditions for the slug flow situation. This particular analysis is quite tough. Since I do not have much time, I will not be going into finding out the acceleration pressure drop for slug flow situations. If any of you are interested, then we can discuss it after the class. Okay. So, therefore, this is the way by which we find out the void fraction and the pressure gradient for the slug flow pattern. Now, one particular correction I forgot to mention. What is that correction? Suppose the bubbles are very large. Do you anticipate any other error might come in which has to be corrected for, and then the corrected alpha, somehow it will affect alpha and it will affect pressure gradient if the bubbles are very long? Do you anticipate anything of that sort for long Taylor bubbles? Say I have got what do you think will happen when we have long Taylor bubbles? Just try to imagine. When we have long Taylor bubbles, what happens? A good amount of liquid will be flowing as films as annular films between the bubble and the wall. Okay. Now, when a good amount of the liquid will be flowing, what do we always assume? We assume that as if the Taylor bubble has occupied the entire cross section. We assume that liquid slugs, they occupy 1 minus alpha portion of the pipe. Can you assume that at that time? There are two things that you have to think. One is liquid, a good amount of liquid flows as a film along the walls. This is number one. So, this influences the calculation of alpha, right? And what is the other thing? If a good significant amount of liquid flows as film, then that significant amount of liquid will that much amount less will flow through the liquid slug, isn't it? So, therefore, normally what do we do? Normally how do we calculate alpha? We assume that more or less the Taylor bubble, it occupies the entire cross section. Alpha, it is calculated by the relative lengths which have been occupied by the Taylor bubble and the liquid slug region. Now, can we do this? Can we write that alpha is equal to this? We cannot do this now. Why? Because in this particular case the actual alpha, this is what, ATB LTB by A into LTB plus LLS. Try to understand this very well. You can find it in books, but concept please try to understand. Do you agree with me? What is ATB? Suppose the liquid film, it is of a constant thickness delta. One thing I assume that for long Taylor bubbles, it is much more easier to assume that the nose region is negligible as compared to the tail region, isn't it? So, one thing we can very safely assume that the liquid film attains or rather it flows as a constant thickness film, as a free falling film which attains a terminal velocity at a particular fixed thickness. Let us take the thickness or the film thickness to be delta. Then in that case, what is ATB equal to? ATB will be equal to pi by 4 into d minus 2 delta whole square. Yes or no? Or in other words, this is going to be pi by 4 d minus 2 delta whole square LTB by pi by 4 d square LTB plus LLS. Yes or no? Do you agree with me? Achha, if this is true, then this can be written down as your 1 minus 2 delta by d whole square LTB by LTB plus LLS. Can I write down the actual alpha? See, when the bubbles are not long, actual alpha is given by this. But now, since the bubble is long and the liquid occupies a significant portion as liquid films, therefore, the alpha actual is this into this. You agree with me? Now, try to understand one particular fact. What is it? Now, we know that if you observe this, again we find that in this particular film region, again by the same logic, the wall shear or there is no particular pressure drop here, isn't it? This entire portion can be assumed to be a region of constant pressure, as I have already discussed. This does not contribute to the pressure gradient. You agree with me? If this does not contribute to the pressure gradient, then we can very well assume or we can imagine that the liquid film here, it almost behaves like a gas, and this entire surface is maintained as a constant pressure in this particular case, isn't it? So, therefore, actually the alpha should be calculated from this particular expression. But we have to remember one thing. What has happened? This LLS is affected just because some amount of liquid from here has gone to the film and is flowing as film. If this particular portion is significant, then LLS will be reduced by a significant portion. By what amount will it be reduced? It will be reduced by an amount which is proportional to this 2 delta by d, isn't it? So, therefore, if the effective alpha prime, what is this effective void fraction which should be considered for long Taylor bubbles? Effective void fraction for long Taylor bubbles. What is this? This is this particular portion, this particular expression. So, therefore, this is equal to the actual expression into 1 minus 2 delta by d whole to the power minus 1. Or in other words, I will write it down here, your alpha prime, this is equal to alpha actual by 1 minus 2 delta by d whole square. Yes or no? You tell me whether you have understood this particular portion or not. Have you understood this particular portion? Yes or no? It is clear? So, therefore, how to find out alpha under this particular condition? In order to find out the effective void fraction, not the actual one, the effective void fraction, you have to remember two things, that since a good amount of liquid is now flowing as film, it is going to affect the liquid slug length here. Okay? But no matter how much liquid flows as film, that will be a region of constant pressure, and therefore, the entire thing can be assumed to be as if a gas mass of constant pressure flowing there, right. So, therefore, under this particular condition, alpha prime can be obtained as I have written down here. But to find out alpha prime, what do you need? You need to know the liquid film thickness. in order to find out liquid film thickness, you also need to know the flow rate of the liquid in the film, isn't it? So, for finding two particular unknowns, you need two equations. Usually one equation you can get from the freely falling film theory. From there you can get one particular equation. From where will you get the other equation? From equation of continuity at this particular portion. Yesterday somebody was asking that actually we should consider QF flowing down, somebody was asking me. So, therefore, you are asking, yeah. So, therefore, when the film thickness is quite significant, we have to do it. There we did not do because the film was very thin. So, therefore, in this particular case, one equation you can obtain from film theory, from the other equation from where you can obtain from equation of continuity. Equation of continuity, okay. From there, what do we know? That the total volumetric flux across any pipe cross section should be constant, or in other words, the total volumetric flux here should be equal to the total volumetric flux here. What is the total volumetric flux here? It is nothing but pi by 4 d square into j. Do you agree with me? This then should be equal to Qg minus Qf in the Taylor bubble region. Agreed? So, from here what do we get? We get Qf, it is nothing but Qg minus pi by 4 d square j. Agreed? Or in other words, this is for this Qg we can write pi by 4 d square 1 minus 2 delta by d whole square, and this into 1.2j plus u infinity, this entire thing gives you Qg, yes or no? This minus pi by 4 d square j, right? From equation of continuity, for the total volumetric flow across any pipe cross section, we can get this particular part. So, from there what do we get? We get Jf. What is that equal to? Qf by pi by 4 d square, correct? So, this will be equal to 1 minus 2 delta by d whole square 1.2 j plus u infinity minus j. Just note this particular expression. Or in other words, if we write it in terms of Jf by u infinity, just to make it non-dimensional, because we are always very fond of making something non-dimensional. So, therefore, in that particular case it becomes something of this sort. Okay. So, we find that we can correlate Jf by u infinity with j by u infinity. J by u infinity we already know. So, therefore, we can find out Jf once we know u infinity. So, therefore, once we can find out Jf, we can find out Qf, and then there is another equation from falling film theory. So, from these two equations we can find out Jf and delta. Once we can find out delta, we can find out the effective lambda prime, alpha prime, which can be used in case the bubbles are long. Agreed? So, these were all the corrections which we could incorporate for vertical slug flow. Vertical slug flow completed. What about horizontal slug flow? In a horizontal pipe, if we take up slug flow pattern, do you anticipate that the same equations that we have derived so long for the last two classes, the same thing is going to happen in this particular case also? Why? Where is the difference? Same pipe, just we have tilted it and made it horizontal. The first thing you have to think that in this particular vertical pipe, the bubble was rising due to buoyancy. Here the buoyancy effect is not there at all. So, therefore, the total dynamics becomes different in this particular case. But since there is no buoyancy, can you say that, well, then there is no relative velocity between bubble and the liquid? That you cannot say. This particular case also, the bubble velocity ub, that will not be equal to j. Okay. So, therefore, the analysis of horizontal slug flow, which I have shown in this particular transparency, this is going to be completely different as compared to your vertical slug flow. Okay. Here we find that there is no drift flux due to buoyancy effects. Therefore, see, the entire analysis there was based on u infinity. Do you understand? What we did, we found out UGJ equals to constant, that UGJ was equal to U infinity. How did that U infinity come? Because the bubble used to rise in a vertical tube due to buoyancy. So, here the basic U infinity concept is not there at all, but UB is not equal to J. So, therefore, how to find out UB in this particular case? Let us see that in this particular case what can we do to find out UB. Since there is no particular relative velocity, there is no particular this buoyancy effect. So, therefore, we can assume that the liquid film at the wall here, that is more or less stationary. Okay, because there is no particular pressure difference, the bubble surface is at constant pressure. So, therefore, since there is no particular pressure difference, we can assume that the liquid film between the bubble and the wall, that is more or less constant, that we can assume. Okay. So, for this particular case, what we know that AB, okay, that is equal to pi by 4 into d minus 2 delta whole square, that we have been doing for a long time. Okay. Again, from continuity of volumetric flux, just like I had done for the case of long bubbles. So, for continuity of volumetric flux at a cross section, what do you know? We know that for continuity UBAB must be equal to J into A. Yes or no? We have made one particular assumption, we have assumed the bubble to be axisymmetric in horizontal flow. Usually that does not happen, particularly for low flow rates, but since the liquid film thicknesses are not very different, we have made this particular assumption here. So, from this what do we get? We get UBAB, this is equal to J into A. Or in other words, we need to find out UB, isn't it? So, this UB can be written down as J into A by AB. Wherever you do not understand, you tell me to repeat it. Or in other words, this can be written down as J into pi by 4 d square by pi by 4 d minus 2 delta whole square. Yes or no? Or in other words, this can be written down as J by 1 minus 2 delta by d whole square. We can write it down. Now, usually what do we know? We know delta is much less than d. We know it. For that particular situation, these things we have been doing for a long time, this can be written down in this particular form. Yes or no? Fine. So, for delta much less than, or rather the film thickness being negligible as compared to the diameter of the tube, the bubble rise velocity can be expressed in this particular form. From here, what do we get? From here we get that UB is greater than J. From this expression we get this, and this automatically proves that the bubble has a velocity relative to the average volumetric flux or relative to the liquid slug. Do you agree with me? Anybody who wants me to repeat any part of this? Or in other words, what is 1 minus alpha equals to? This is nothing but 1 minus AB by A. What is AB by A? AB by A equals to J by UB. So, this is equals to 1 minus J by, 1 minus J by UB, isn't it? So, therefore, what do we find? That in order to find out alpha, again we can, what is important? U infinity is, there is no U infinity here, UB is important. Again UB, it can be defined in terms of certain dimensionless parameters considering the forces which are acting on the bubble here. Again we can say that gas density, gas viscosity, they are negligible. Okay, so, what are the important forces, and by balance of those forces, what are the important groups that we get? Same thing will be there, inertia is going to be important, surface tension is going to be important, your viscosity is going to be important, only buoyancy might not be so very important. Okay. So, we find that from dimensional analysis, okay, in the absence of effects due to gas viscosity and gas inertia, if we neglect these two things, so then for bubbles which move independently, that means they are not falling into each other's wake, or in other words the liquid slugs are large enough. For such circumstances, we find what are the important dimensionless parameters which govern this. One dimensionless parameter is definitely J by UB. Fine, because we have already got it. that decides. So, this is nothing, it is just the liquid velocity in slug divided by the bubble velocity. Definitely one liquid slug Reynolds number is going to come here, okay, that has to be important, which is J d rho L by mu L. This is going to be something very important here. Then viscous force, surface tension forces, they have to be important. So, J mu L by sigma, this another important thing, viscous force by surface tension forces. And when will this slug flow not happen? When buoyancy becomes important and the entire gas goes up. Okay. So, therefore, in order to decide the limit of this slug flow pattern, your buoyancy by surface tension, this particular term also has to be important. Mostly we will find that these three terms will be governing and the limit of slug flow will be governed by this particular term. Do you agree with me? If you notice these terms, you find that more or less these three terms particularly, they more or less correspond to the dimensionless groups which we had obtained for vertical slug flow. There also it was buoyancy by surface tension, buoyancy by viscosity, buoyancy by inertia. More or less these terms also correspond to an identical balance of forces which we had obtained for the vertical slug flow case as well. Okay. So, therefore, we find that again what we would like to do, we would like to remove J from one particular thing. So, we can combine these two to form a property, liquid property group, and usually we find that more or less this J by UB, that is plotted as a function of J d rho L by mu L. It is plotted as a function of this, very sorry, it is plotted as J mu L by sigma L, okay, with one particular parameter lambda, where lambda is mu L square by d rho L sigma. This particular lambda is obtained by eliminating J from these two terms. Okay. Now, this particular graph is usually obtained, and from this particular graph, from the type of graph we get, we try to find out, we know J, so we try to find out UB from here. Once we can find out UB from here, then we can find out 1 minus alpha, and then we can go to predict the pressure gradient, right. Now, certain things you have to remember in this particular case. What are those certain things? Usually we find that a graph which has been obtained for very low velocity, when the velocity is very low, then J is almost equal to UB, isn't it? When the velocity is very low, then J is almost equal to UB, or in other words, J by UB, that is almost equal to 1, and if J by UB is equal to 1, then in that case delta has to be much less than 1. Do you agree with me? So, at low velocities what happens, J is equal to UB almost, this implies delta has to be much less than D. Okay. So, we find that at low velocities J is almost equal to UB and delta by D, it is much less than 1. And at high velocities what happens? When the velocity is high, then definitely J by UB cannot be equal to 1. We have observed that at high velocities, or in other words at high Reynolds number, REL greater than 8000, for this particular situations we have found usually J by UB that reduces to a value of 0.84. Clear? This people have obtained by experiments. Usually if you plot this graph, we find that this graph starts from 1.0 and it reaches the asymptotic value at about 0.84. Okay. So, if J by UB is equals to 0.84, then in that case what is UB equals to? It is almost 1.19 J, correct, which is close to about 1.2 J, the value which we have obtained for vertical slug flow. This is obtained for REJ greater than 8000, correct. So, for those particular cases UB, this is equals to 1.2 QL plus QG by A, isn't it? What is alpha? It is JG by UG, or this is equal to JG by UB, correct. So, therefore, what is this equal to? This will naturally be equal to 0.84 Qg by Qg plus Ql. Do you agree with me, yes or no? This horizontal slug flow part, is it clear to you? What did we do in this particular case? We found ub is not equal to j, and how to we need to find out ub, because ub decides alpha and 1 minus alpha. This alpha and 1 minus alpha have to be substituted in the pressure gradient calculations. So, how to do this? We have to find out j by ub. Again we resort to dimensional analysis, and we find that usually we work with these three particular dimensionless groups, where one of them contains ub and one of them is just a property group. Okay. From there people have found out that when the velocity is low, then both the particular velocities, or rather both the liquid and the bubble, they flow at the same velocity, or more or less j can be approximated to be equal to ub, which automatically implies that this is possible only when the liquid film thickness is very small. Okay. This occurs at low velocity. When velocity is high, that means the liquid Reynolds number is high. Under that particular case, people have observed that j by ub reduces to a ratio of 0.84, which gives you ub equals to almost about 1.2 j. If this is substituted in the expression of alpha, we find that alpha can be obtained by this particular expression. Now, this alpha, if it is substituted into the pressure gradient expression, then we can get the accurate pressure gradient expression. But remember, in this particular pressure gradient is not very simple. Why? Because it primarily comprises of the frictional pressure gradient, it does not comprise of anything else. If you have to calculate the frictional pressure gradient, you need to know the relative lengths of the liquid bubbles as well as Taylor bubbles as well as the liquid slugs, because with the same particular velocity we can have different combinations of lengths of the liquid slug and the Taylor bubble. So, unless you know that, it is difficult to find out the frictional pressure gradient. Okay. So, these are these few things which I wanted to say. I also wanted to cover the annular flow pattern. Probably I will not get a time for it. From the next class you will be studying boiling and condensation, and after that I will be taking a few more classes on the measurement systems in two-phase flow. If time permits at the end, then I will come back to the annular flow pattern. I will discuss a few portion of it, or else you can refer the web course to find out the details of horizontal slug flow, the pressure drop part as well as the annular flow part. Thank you very much.